Hi, welcome back to Math 234. I'm still your host, Steve Dragoo. All this week, which is just two lectures, we've got Stokes' theorem, which is section 16.8, and it's a doozy. So, I suppose, just kind of dive right into it. So, step number the first, we need to recall all three of the last sections that we've done. So Green's theorem, curl and divergence, and surface integrals, because we're putting all three together to make Big Daddy Stokes' theorem. So, as a quick reminder of what the old set was, what the thing we were doing had been. Oh, okay, never mind. Fine. Green's theorem. It's there at the top. It's the thing with that K highlighted, right? Green's theorem says that if we take the closed loop integral of f dot dr around the boundary of some two-dimensional surface, some flat two-dimensional region, that's equal to the double integral of qx minus py. And we expanded on qx minus py to say that that's really just the third component of the curl. Right, our three components of a curl, which I suppose I could pull up over here on the right. Qx minus py is this third component over here. Q partial x, p partial y. So a fancier way of writing that thing is to say it's just the curl f dotted with k. Where k is just the unit vector pointing in the upward z direction. Stokes' theorem wants to update that to, instead of just being a flat two-dimensional region, to be some sort of flat two-dimensional surface, but that curves through three space. So we're still going to be looking at comparing a double integral of a thin surface, but now we're going to let that surface exist out in three space instead of being stuck only to two dimensions. So where Green's theorem deals only with vector fields that have two components, so an x and a y component, and again, we'll just be in a flat region. Stokes' theorem is basically that same thing, but updating it to being able to work in three space. So we can bring our z component back. But if we come to analyzing what that k vector was in relation to our flat double integral, k is just the normal vector of a flat surface, right? It points straight up, points in the z direction. If my region is flat, if it's just in the xy plane, then k is the normal vector. In particular, it's the unit normal vector, because k has a value of 1. So Stokes' theorem will update that vector k to just be the unit normal vector of our surface. And specifically, we want it to be the upward pointing unit normal vector. Because orientation, it turns out, is rather important for these surfaces and the curves that go around their boundaries. So we had the idea of an oriented surface last time. We looked at surface integrals. Those will be coming back because that second half, or that right half of Stokes' theorem, the part that is a double integral, that is going to be a surface integral. So we're integrating over some surface S. So oftentimes we'll write out that ds as a vector quantity. So ds with the vector hat over the top of S at the end of it. But it can also be separated out into the unit normal vector times ds. So bringing back the right hand rule, and there are, of course, two versions of the right hand rule. One that talks about the order of the three axes, right, where you stick your three fingers out in the three different directions, gets you one version of the right hand rule. The other is the one you can see on screen where you curl your fingers around something that's going around in a loop, or something that has a curling direction. something like a positive or negatively oriented curve. If you do that, stick your fingers in the order of, or in the direction of rotation. Your thumb will point in the positive direction. So we're going to use this curling right hand rule to determine the correct or the positive orientation for our normal vector. So again, from back in Green's theorem, we defined two different orientations for curves, and we're mostly still going to work with those. We still want to think of counterclockwise as the positive direction with negative as the clockwise direction, but it gets a little more nuanced once we enter three space because now those curves could be viewed from a number of different angles. So wherever possible, we'll look down at a curve. So we'll say it's counterclockwise when viewed from above. Cool. Quick note on the normal vector. It's usually going to be the cross product of two partial derivative vectors divided by the magnitude of that cross product. Or we'll go back to our explicit version of the normal vector where we can. This first example was kind of boring because everything just worked out to 0. So we won't see much if we do that. Instead, I want to come back to this page out of the textbook. I think I've brought it up a few times, but we're going to keep going with it because pretty much everything we do in chapter 16 is some version of the fundamental theorem of calculus. And that includes Stokes' theorem. It is just a retelling of that fundamental theorem of calculus. Again, fundamental theorem is the one that says if I take an integral that's just equal to f of b minus f of a, the thing that we do whenever we want to evaluate some integral. All the way back in Calc 1, our region of integration was just an interval, right? Some line segment from A to B. There is a curve that usually goes above that line interval. But as far as like the x values that I'm integrating over, dx just goes along some straight line interval. We then, of course, had the fundamental theorem for line integrals, which is very similar to the original fundamental theorem. It just says that we can also pass our differential through some curved line. It didn't need to be straight, but it works out to be basically the same thing. It's f of b minus f of a. With the next two versions of the fundamental theorem that we have, which are Green's theorem and Stokes' theorem, they still spiritually embody this fundamental theorem, though it looks quite a bit different. But if we pay attention to the number of integrals that we're doing, our integral count always goes down by 1. So in the original fundamental theorem, we have a single integral, and we go down to 0 integrals. We said it equals something that is 0 integrals. And with both Green's and Stokes' theorem, this time we'll start with a double integral and reduce that down to a single line integral. So our integral count goes down by 1. And if I start trying to talk about what was so important about f of b minus f of a, well, if we head back to our line segment, a and b are simply the boundary points of that interval. But specifically, I want to focus on the fact that those 2 points are the boundary of the interval. Because when we step this thing up to integrating over a region, right, where we have a double integral over a region, the line integral that goes down to is over the boundary to the region. So in all versions of the fundamental theorem of calculus, we equate some integral to an evaluation at its boundary. And that's exactly what Green's and Stokes' theorems are going to try to do. We'll say that a double integral through the region, or a surface integral across the surface, is equal to just a line integral along the boundary curve of that region. And again, Green's and Stokes, hopefully the image is doing some amount of work for explaining the difference between the two of them. Green's will apply specifically to flat regions, so stuff that's just in the xy plane. We don't need to involve 3 space for Green's theorem, but Stokes' theorem takes that same idea and just upgrades it to 3 space. So now my surface can be curved instead of needing to be flat. And there's one final theorem that we'll talk about that works for triple integrals in the fundamental theorem of calculus. But that's the week after this one. So with all that said and out of the way, let me just double check there wasn't anything else I needed to bring up over here. Nah, I think we're good. So let's go do an example of this stuff. So what do we want? Stokes theorem. We want to use it to compute the integral, which is the surface integral of the curl of f dot ds, where f is the field provided, and s is the part of the sphere, x squared plus y squared plus z squared, that lies inside the cylinder, x squared plus y squared equals 1, and above the xy plane. You can see the image sketched over there on the left. We want that blue surface. And when it comes to evaluating Stokes' theorem, when it comes to solving a problem that says use Stokes' theorem to compute something, you should always do the opposite of whatever we tell you to do. If we ask a question that says use Stokes' theorem to compute a double integral, I know with a high amount of certainty, I am definitely not going to calculate a double integral. Stokes' theorem has the two sides to it, right? There's a double integral being equal to a line integral. And just knowing the way that we write problems that are interesting for you to either learn the material or get quizzed on the material, you're going to do it the opposite way of what we say. So since this thing says to compute the double integral, I'll be computing the line integral instead. So my first thought is to just write that down. So the double integral over my surface of curl of f dot ds is equal to the line integral, and let's call it just partial s for the boundary of that region of f dot dr, which I could even again rewrite for funsies. Says this thing is just the integral along the curve C of f of r of t times r prime of t dt. So don't forget that little circle in the middle of an integral sign is just giving us the extra information that our curve is closed, right? When we put a little circle in a line integral, it is implying that the thing we're integrating over is a closed loop with positive orientation, but it doesn't mean anything aside from that. Aside from just looking different, it's still just an integral sign. So don't let yourself get tripped up by that notation. So I'll just keep using it so that we grow accustomed to it. Right. We want the dot product of our field, which we have, and the derivative of some sort of parameterization of that curve. So our surface, again, is that part of the sphere, but its boundary curve is going to be the intersection of the sphere with the cylinder. So that's the thing that I want to parameterize. That cylinder, x squared plus y squared is equal to 1, means that if I intersect it with the sphere, x squared plus y squared plus z squared equals 4, I'll just get the equation 1 plus z squared equals 4. Since x squared and y squared added together are 1. So I can solve this thing for z. Looks like z squared is equal to 3, which means that z is plus or minus the square root of 3. But we're above the xy plane, so z is going to be the positive square root of 3. So I've got that part together. Then let's go parameterize that curve. It's a circle, right? I'm going around my surface, which is just a part of the sphere intersected with that cylinder. So I think a good parameterization for us to use is going to be r of t is equal to our pretty standard choices for a circle. Cosine t for x, sine t for y, and the square root of 3 for z. because we just solved that part. Since our circle's got a radius of 1, don't need to worry about an extra radius term added on top of that, or multiplied on top of that, I suppose. Don't forget, though, anytime you make a parameterization, you should include bounds for your parameter. In this case, we just have 0 to 2 pi for t, because it's supposed to be a theta stand-in. So now I want r prime. R prime of t is going to be negative sine t, cosine t, 0. And then I'll just go plug all that stuff into my line integral. So I suppose while we're right here, I'll just write it down. F of r of t. That's because I can see everything on screen from here. If I plug in everything for x and for y and for z, what do we have? X is cosine t times the square root of 3 times the square root of 3. Close enough. YZ is going to be sine t times the square root of 3. Maybe I'll put some parentheses around those. And the r component, x times y, that's just cosine t sine t. And I could use a little bit more space. Cosine t sine t. All right, then this thing is equal to the integral of 0 to 2 pi of f of r of t dotted with r prime of t, this guy. dt. So I can give you a second to write that down while I just go, let's copy and paste and put this stuff back. One right there. There. And I would like to move that 0 out of the way. Just simplify that dot product before I try to integrate this thing. 0 to 2 pi. Let's see, what do we get? I've got a negative square root 3 cosine t times sine of t for the first component. I've got the square root of 3 times sine of t times cosine of t for the second component, and 0 for the third component. Since anything times 0 is 0. So negative 3 cosine t sine t plus square root 3 cosine t sine t. That just adds up to 0. So even before I integrated, I saw that my integrand was 0. So not a lot of work to do on the integrating part. Cool. So if we come back to that curve, so I suppose didn't entirely talk about it in the moment, but probably worth bringing back. We do want to make sure that this thing is positively oriented, which means if we use our right hand rule, our thumb should point up because we want the upward pointing normal vector when we talk about evaluating Stokes' theorem in any which way. And we can see that if our normal vector is to point up, then that curve should go counterclockwise when viewed from above. So we did, in fact, go with a counterclockwise parameterization of the curve. So if we go cosine t sine t, that's going to be counterclockwise. Since our normal setup for cosine t and sine of t is already counterclockwise. All right, just like the unit circle was. But all right, let's go check out another one. So this time we're going to get the line integral of f dot dr, where f is the field, y is the x, and c is the unit square shown to the right. Again, whatever we explicitly tell you to do, you should do the opposite. So this thing's telling us that we should do the line integral. So we're going to use Stokes' theorem to convert that to a surface integral. F dot dr over c. Stokes' theorem tells us that that is a surface integral of curl f dotted with ds. Or let's go ahead and just call that n ds. And we'll bring a few ideas in together over here. So first up, I would like to get the curl. So the curl of f, which has an L before the parentheses. All right, if I go back to what that thing was defined as, it's going to be a vector quantity, and it's going to involve p, q, and r, and also partial derivatives with respect to x, y, and z, all in some order. Easiest way for me to remember this stuff is that P, Q, and R all go in reverse alphabetical order. So this is going to be R, R, then Q, then P, then R, then Q, then P. And then the X, Y, and Z letters all go in their regular alphabetical order. But remember that you can't pair up any letters with their correct positioning. So I can't have any x partials in the x component. So this thing starts with a y derivative. So r partial y, q partial z, p partial z, r partial x, q partial x, and p partial y. Subtraction, comma, subtraction, comma, subtraction. So that's the curl order. Where to put some stuff together. P is the first guy. That one's PQ. It's the second component. And R is the Z component. So let's write down what that curl is going to be. So R partial y. So that's x partial y, which is 0 minus QZ. Z partial z is 1. 0 minus 1. Then PZ. That's going to be y partial z, which is 0 minus Rx. X partial x is 1. Thirdly, Qx. Z partial x is 0 minus Py. Y partial y is 1. So our curl looks like it's going to be -1, -1, -1. So let's head over to that unit square and look that it is giving us an orientation already. Right? The unit square is oriented, or at least that curve, the loop that goes around it is oriented. So we need to come up with a normal vector that matches that orientation. So go to the right-hand rule, make sure that you curl your fingers in the direction that we're going around. And you should find that if you orient that correctly, your thumb is pointing out of the page. It's pointing in the positive x direction. Here, if you're taking a look at that, it's again, it kind of looks sort of like that. Make sure you use your right hand for the right hand rule. You'll get it backwards if you use your left hand. So, you know, whatever it takes to make sure you know left from right. Go with your right hand. And again, we should hopefully find a normal vector that points in that positive x direction. So n is going to be this vector right there. It should be a unit vector. So this is going to be 1, 0, 0. And then we can go calculate that thing. So we have the double integral of the curl of f, which is -1, -1, -1, dotted with our unit normal vector 1, 0, 0, ds integrating over the surface S. And that simplifies rather nicely. That's just -1 ds. So much like the double integral of dA gives the area of a region, the double integral of ds over S gives the surface area of a surface. Our particular surface is just a flat square. So I think that the double integral of ds should be equal, again, to the double integral of dA, since our surface is just a flat square. So that is going to be -1 times the area of a square. Area of a square. And the area of our square is just 1. Right, it is the unit square, side lengths of 1 in both directions. At least, I hope it's the same in both directions, since that's what makes it a square. 1 times 1. So, wherever possible, we'll try and take the easy path when evaluating integrals, since there's a lot of other work to go in surrounding these integrals that we're doing. But if memory serves, I think the next one, we get something a bit more exciting. Yep, I think we do. Okay, so evaluate the line integral f dot dr, where f is the field. Well, it's right there, -y squared plus x plus z squared. The curve of intersection is the part of the plane intersecting with that cylinder. And we, of course, want to make sure that C is oriented counterclockwise when viewed from above. So if we view that curve counterclockwise from above, and we just pick the nice looking surface S right there. Our normal vector should point in the upward direction. Right? It does not mean that our normal vector will point straight up, just that it will point upward. Right? If I've got some vector in 3 space and I want to figure out if it has an upward orientation or if it has an upward direction, I need to only look at its z component. Because z is the up and down direction. So if I want something to be pointing upward, I just need to check its z component and make sure that that's positive. So we'll be looking at r to make sure it points in the correct direction. But right, we're back to evaluating a line integral, and because this is Stokes' theorem, we do the opposite of what we're told. So the integral of f dot dr is going to be a surface integral of a curl of f ds over some surface S. And let's go at it from there. What do we want? A curl. Let's go calculate one. Curl of f. Again, R, Q, P, R, Q, P. Close my vector. Partial derivatives should go in alphabetical order. So y, z, and then z, x, and then xy. Subtraction, comma, subtraction, comma, subtraction. So I get something fancy. Let's go figure out what that should be. We have our partial y. So z squared partial y is 0. QZ, x partial z is also 0. So nothing in that first component. P partial z, so that's negative y squared partial z is 0 minus r partial x, which is z squared partial x, also 0. Nothing too exciting going on there. Then qx, so qx partial x is 1 minus py, negative y squared partial y is going to be plus 2y. Right? Double negative is going to make that thing positive. Then we want to come up with a normal vector because we're going to be integrating a surface. We're going to be evaluating a surface integral where we have an explicit function. Right? It looks like the thing that we're going to want to integrate, or the surface that we're going to want to integrate on, is that plane, which planes can be an explicit function. In particular, my surface S. It is z equals g of x and y, because it's an explicit surface, and it's just 2 minus y. Right, that's my surface right over here. Y plus z is equal to 2. So I can solve that thing for z and just have an explicit function. Now that it's time to actually evaluate a surface integral for real, let's just pop backwards in the notes real quick because I want to go borrow a formula. We are going to be taking the surface integral of a vector function. So if we have that, an explicit vector function, the surface integral of f dot n ds is just the dot product of f with either the positive or negative version of that vector field. Negative g partial x, negative g partial y, positive 1. So, yeah, I'll just grab the whole thing. So we want to use that to help us integrate the thing that we're on right now. So let's take that back over to today's notes. And I think we're going to need to just slide this down a little bit. And paste. Right, this is what n should be. Our vector n. It should be plus or minus g partial x, negative g partial x, negative g partial y, positive 1. And actually, you know what? Bring you back over here because I'll have more space this way. I don't need the dA attached to n though. I'll pull that back in later. So, what do we have? G partial x, 2y, 2 minus y, partial x, that's 0. Minus g partial y is negative 1. And then 1 for the z component. All right, so remember that we do want to make sure that our normal vector points upward because that matches the orientation of our curve. But if we follow that thing counterclockwise and viewed from above, our normal vector should point upward. So I'm paying specific attention to the z components of that normal vector. Just need to look at the third component, that positive 1, and make sure that that number is positive. But with the way that I've written out that normal vector, it is already predisposed to pick out the positive or the upwardly oriented normal vector. So with all that said, we're probably ready to integrate this thing. One quick comment before we go to that. All we wanted was a normal vector in order to make this integral come together, the surface integral come together. And the surface that we're integrating is a plane. And planes have very easy to identify normal vectors. Right, you just need to look at the coefficients on the plane when it's in its standard form. So 0x plus 1y plus 1z. I think pretty easily from that plane, you could pick out the normal vector as 0, 1, 1. Right? Because again, it is a plane. We know how to find the normal vectors of planes. Since we're nearing the cumulative final exam, it's not a bad idea to sprinkle in a little review from time to time. Yeah, so 0, 1, 1 is the normal vector we should have gotten. And fortunately, we can see that that's what we got by using the formula. 0, negative, negative 1 is positive 1, and then 1 again. But let's plug some stuff in. We are after the double integral of that curl 0, 0, 1 plus 2y dotted with our positively oriented normal vector 0, 1, 1. Makes sure that it's positively oriented. We've switched over to integrating an explicit function, which means we're changing our surface integral to just a standard double integral. So our differential is dA now, and we're going to be integrating over some flat region D, which will be a projection of our surface down into the xy plane. Right, with explicit surface integrals, we take our surface and we project it down to the xy plane. So if you look over to the diagram on the right, you can see that all of these parts are labeled, both C being the boundary curve of the surface, S being the surface we want to integrate, and then that projection of S down to the xy plane is D. I think a lot of that is a bit pedantic, which is, yeah, totally fair. But I'll at least do my best to keep things written out the proper way. So if you ever go look at the notes, it'll at least all be done up proper, even if, half the time you cannot pay attention to a bunch of that information and still arrive at the right answer anyway. It'll take a fair amount of getting used to before you get all of those letters right every time. Trust me, I would know. But right, let's see. We take a dot product and let's go figure out what our dot product is going to be. Actually, now that I look at it, I'm running out of space. So maybe let me slide you over here, squish you a little bit. And write down what this thing is equal to now, but with not the worst integral s's I've ever seen. We're over some flat region. This is 1 plus 2y dA. And our region is a circle. Right, D is a circle. It was projected down into the xy plane. We're intersecting that thing with the cylinder, x squared plus y squared equals 1. So D, the projection down into the xy plane, is a circle with a radius of 1 centered at the origin, oftentimes just called the unit circle. So this will be 1 plus 2r sine of theta times r dr d theta. Dr d theta. Theta goes from 0 to 2 pi, r from 0 to 1. And we'll come up with some answers for that mess. So first thing first, If I look at doing the theta integral on that second term, right, 2r sine theta, I'll be taking sine theta on a trip all the way around the circle. So if I do that for sine of theta, I know my result is going to end up at 0. Sine of theta is going to have just as many positive quadrants as it'll have negative quadrants. So the integral of sine theta over its full period always comes out to 0. So the second term on there is going to be 0. I only need to look at integrating the 1 part. So don't forget that 1 is going to be multiplied by r. So that's going to be 2 pi times the integral of r, which is r squared over 2, evaluated from 0 to 1 is just 1. Plus, again, the other part's theta bit integrates to 0. So I don't even need to worry about the r part. I know that bit is going to be 0. And I just get pi. And since I'm effectively splitting this thing up into the integral of 1 dA plus 2r sine theta r dr d theta, and again, that sine theta part will be 0. So, 2 quick comments. One, if we tried to do the line integral part, well, it's doable, right? Because it is just going to be this line integral going all the way across, which is not too bad. Sine cubed, right? If we just kind of look at doing that, sine cubed is going to integrate to 0. Cosine t will integrate to 0. That integrates to 0, and that integrates to 0. Since all of those are symmetric functions going over a full circle. So the only thing that survives the integral process is cosine squared, and it's got a value of pi. So it'll come out to the same answer. But I also think that that integral is a bit more involved. And maybe if you're a little shaky on some of your geometric interpretations of trigonometric integrals, that doesn't look as easy to you as it did to me. Yeah, that could be totally fair. The main point I'm trying to make is that I think doing this double integral side of Stokes' theorem was easier than doing the line integral side of Stokes' theorem. Stokes' theorem is often about just trying to choose the easier method to integrate. And again, just knowing the way that we write questions to test whether or not you know the math, we'll write a question that just asks you to do it the hard way, and then you'll have to know you should switch to doing it the easy way. But be prepared for every time we ask a question about Stokes' theorem that we'll be stating the hard way. You should switch and do the easy way. Now, the surface in this example is not unique. So what do we mean by that? Well, probably a couple of things. In fact, in both of these two examples, the surfaces that we picked are not unique. All we were told is that C is the curve of intersection between the plane and the cylinder. We weren't told specifically what our surface is. All we know is the curve. Because I think we could actually attach two different surfaces to C and have them both work out the same, right? There's the very obvious plane surface, the one that we integrated over, because that seemed rather nice. So that's the one that we picked, just integrating that blue part. But if you look at the gray part, the part that is the cylinder, and that also includes that flat projection area D, so like that circle down in the XY plane, attached to the cylinder, and then ignore that blue top. But that gray surface also has a boundary that is C. So either one of those two surfaces could be the extension from the boundary curve C, and we should find that the Stokes theorem integrals come out to the same value in both ways. Which is maybe a bit odd to think about. But if we go back to our idea about the fundamental theorem of line integrals, we said that the thing that was interesting about those is that the integral itself was path independent. It did not matter the path we took to get from one endpoint to the other. I could just evaluate the thing at the two boundary points and call it a day. So those line integrals were path independent, the fundamental theorem of line integrals. Now that we're doing the fundamental theorem of surface integrals, with some air quotes added in there, that's Stokes' theorem instead. But it's also going to be surface independent. Whatever my boundary curve is, I could attach any surface to that as long as it's a nice kind of surface, which we won't try to unpack that statement. Let's just say that these surfaces are going to be nice. So I can attach any surface I want to the curve, and I should find that the integral comes out the same. Same thing up here. We weren't actually told a surface to integrate on for this curve. We were just told C is the unit square, but we picked the most obvious surface, or maybe just the easiest to work with surface, which was the flat square enclosed inside of that curve. But I could go and attach any surface I like to this curve as long as its boundary is that square. Which means that on occasion, if we're looking to solve some surface integral, it might be easier to just attach a nicer surface to our boundary curve than the one that we're given. And hey, look, doesn't that lead conveniently into this next example? So S is going to be a surface formed by capping the piece of the cylinder, equation given there, with the top half of the sphere, x squared plus y squared plus z minus 4, quantity squared equals 2. Step number the first is to draw a rough sketch of S. So, that's not what I wanted. That's really not what I wanted. Come on, draw, there we go. A cylinder. The way that I'm going to draw this cylinder is by copying and pasting that little diagram. Cool. So I think that's straight down. Cool. There's my cylinder. I need to attach a sphere to it. Sphere will look like a circle on its side profile. So let's do that. All right, cool. Roughly, I mean, that's actually a pretty solid sketch, I think. That's what our surface is going to be. Is that shape. Right, we're just taking the top half of the sphere and sticking it on top of the cylinder. Bearing in mind that that sphere should have a center of 0, 0, 4. Gray out those parts. So I'm mostly paying attention to the x or the z component, right? That thing is the equation of a sphere, but shifted to a center of 0, 0, 4. So the question we want to ask is what actually is the boundary curve of this surface? So my cylinder is the part that, wraps all the way around, right? It's the outer shell of that cylinder. The top has been capped. It's got that sphere up there, meaning the surface is closed all the way up top. So our boundary curve is just this part down here. Really, it's not filled in. The boundary curve is just that part. Right, that's my boundary curve. That's delta S. Or partial S, or whatever that symbol is. DS, it's this thing. Well, So we want to parameterize this curve so that it has positive orientation with respect to its outward normal. So out, if I'm coming out the sides, definitely is going to be out this way. But as I move up to the sphere, out is still pointing up. So our right-hand rule tells us that in order to have an upward pointing normal vector, we should still be going counterclockwise around that circle. So C should be the curve R of t. It's a parametric curve. It's going to be root 2 cosine t, root 2 sine t, and then 0 for the z component because it's down on the bottom. T is, of course, in 0 to 2 pi. And I know I'm over on time, so I'll pause right here. So again, if you've got, hold on one second. Bye, 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 bye. Okay, and we are back. So let's finish out this problem real quick. So we've got our curve. We might as well also come up with our prime right here. It is negative root 2 sine of t, positive root 2 cosine of t, 0. And then we want to evaluate the surface integral, curl f dot ds, where f is that field. But since it told us to do the surface integral, we're gonna not do that. And instead use Stokes' theorem to say that curl f dot ds is equal to the closed loop integral around the boundary curve of that surface of f dot dr, which is going to be, maybe come back up here and focus on that 0 that I have for z, right? Because the z component of our curve is 0, which means that every term with a z in it is 0, conveniently. So this thing looks like 0 plus 0 plus x for the first component, 0 plus y for the second component, and 0 for the third component. Each of these 4 zeros all come from that fact that the z component is 0. Which means right away, our field looks a lot nicer after plugging in our parameterization. And I want the dot product of that with the leftover part, negative 2 or negative root 2 sine of t, positive square root 2 cosine t, 0 dt. Squish that so that it actually fits on the page. I know that t is going from 0 to 2 pi, so I'll plug those parts in. And then I left the x and the y parameterizations alone for a second because I really wanted to just focus on the fact that all of that z stuff went to 0. But when I take the dot product, I will finish substituting my parameterization curve in. So x, I know, is root 2 cosine t. So this is going to become negative 2 cosine t sine t. Right, the cosine t comes from the x part that I needed to finish substituting in, and I'll have square root of 2 times square root of 2 to just be 2. Plus, on the other hand, y is root 2 sine t, so this is going to be 2 sine t cosine t. Plus 0 times 0 is 0, dt. And hey, look, negative 2 cosine t sine t plus 2 sine t cosine t. That inside bit is 0, so the integral of 0 is 0. almost everything went to 0 today. I think next time we'll see even more examples that are going to be just as fun. All right, for real, signing off now. Okay, bye, 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 bye.